Hello everyone. In today's video, we're going to be talking about the angular momentum. As we mentioned in the previous video on linear momentum, the word momentum means the quantity of movement or motion of a body. So the angular momentum is not very different from the linear momentum. It's basically mv, which is the linear momentum, multiplied by the radius r. V is also equal to r theta prime, and we know that from this image right here. Delta S, or S, is equal to r theta. S is a distance, it's an arc. So if we want to find the velocity, we're going to have to find the first derivative of S, because ds by dt is equal to v. So the first derivative of S is r prime theta plus theta prime r. R prime theta is obviously equal to 0 because r is a constant, r prime is thus equal to 0, and v becomes equal to r theta prime. And I suggest writing these steps down on a paper so you can visualize and understand the concept better. And now we have two r's in this formula right here. So mr squared is equal to the moment of inertia I, because the moment of inertia of a particle rotating around an axis is mr squared. Now for the angular momentum of a system rotating around a fixed axis. Now, at this point, we have to recognize certain patterns or certain recurring themes, and the idea of a system is very recurring. So when we have a system, we immediately know that in most cases, we have to add certain quantities. So when we had the linear momentum of the system was the summation of the individual linear momenta, and similarly here, the angular momentum of the system is the sum of the angular momentum of each particle on its own. Now, in case of a solid, we know that solid means there's a firm system, so it's moving with the same theta prime or the same angular velocity. So sigma, or the angular momentum, is equal to the summation of I theta prime. Theta prime is factorized since, as we just mentioned, it's common between all particles. All particles are moving with the same angular velocity, the same theta prime. And so we end up with this formula right here. Now for the theorem of angular momentum. Now, before we discuss this in details, I just have to point out one thing. As we mentioned previously, there are certain parallels or parallel themes or patterns between rotational and translational motion. And that can also be said about the angular and linear momentum. The linear momentum, we usually talk about external forces. So if the linear momentum is conserved, that means that the system is isolated, so there are no external forces acting on the system. Now, similarly, in the case of angular momentum, it's conserved right here if we've got no external moment or torque. Now the moment, let's discuss it before talking about this formula. The moment, or the torque, is the force applied across the lever arm. The lever arm is also known as the perpendicular distance to the force applied on the object. Now, if we find the first derivative of sigma, or the angular momentum, we can move step by step here, and we end up with I theta double prime, which is the second derivative of theta. And so the summation of the moments right here is equal to d theta by dt. And it is worth noting that here we take the moment of inertia outside of the first derivative because we consider it to be a constant. So now for the conservation of angular momentum. As we just said, the angular momentum is conserved when the moment, or the torque, external to the system is equal to 0. So first, we talk about the case of a deformable system whose moment of inertia is variable. So let's consider that the moment of inertia is variable. How is it variable? We can see that in this figure right here. In the first part, the girl spreads out her arms and she's rotating with a large moment of inertia. Because if we consider this to be a particle, and then we take the standard mr squared formula of the moment of inertia, r here, or the radius, is at a maximum distance from the fixed axis, which is the body of this skater. Whereas in the second image, the girl moves her arms inside, and so the moment of inertia becomes small because the radius is no longer large. So in this case, the moment of inertia is variable because it changed, it is not constant, and thus the summation of the moment is equal to 0, and d theta by dt is equal to 0 because the summation is equal to d theta by dt. Now, in the case of a deformable system whose moment of inertia is constant. Now, if we've got a constant moment of inertia, the system is deformable, but it is not of a variable inertia. It is constant. So the summation of the moment remains equal to 0. But when we equate the sigma I to sigma f, which is the initial angular momentum, to the final angular momentum, we end up with this formula right here, which means that I1 theta 1 prime is equal to minus I2 theta 2 prime. But we have to keep in mind that I is constant. So really what's varying is the angular velocity theta prime. And that is all we have for today's video. But for more information on moment and the torque, tune in for future videos because that will probably be discussed in more details later on.